calculating Ka or pKa or Kb or pKb, okay, and Ka, pKa have a relationship of the same as hydronium ion to pH, okay, which means that you take the negative log of Ka to give you the pKa, and the same for Kb and pKb. So the first question here, you discovered a new acid, woohoo, and that is Hz. And so that's the new acid, and the important part about Hz here, because it tells you that it is monoprotic, only one dissociated hydrogen here. So that's why it's important to know it's Hz. The pH of a 0.100 molar solution of this acid is 3.12. What are the Ka and the pKa for this acid? Okay, so in order to do this, we need to go ahead and first take the antilog of 0.01, because that's going to give us the concentration of the ions in there. Okay, so then 7.59 times 10 to the negative 4 molar. Okay, now in these problems we are working opposite to what we did before when we were actually calculating pH. Okay, so this is the reverse of that. So anyhow, let's set up our equation. You still have to do this. Okay, and plus H2O. I'm going to start writing my H2O from now on, okay, so that we don't have any confusions. And then Z minus is our conjugate base here. Initial concentration here, okay, for the acid is 0.01. So 0.01 is the initial concentration here. The initial concentration for our hydronium ion concentration is 7.59. times 10 to the negative 4. And how is that? That's because we were given the pH. Okay, if you were not given the pH, then things would be a little bit different. All right, but because we're given the pH, we know that the hydronium ion concentration is 7.59 times 10 to the negative 4, and the conjugate base also is going to be the same. All right, so 7.59 times 10 to the negative 4. Okay, and I'm sorry, just want to say one thing over here. This is not the initial, this is after dissociation. Okay, because you started with this, so the change here is going to be the minus 7.59 times 10 to the negative 4, and the change here is the plus 7.59, because that's the pH. So after dissociation, that's the concentration you get. So initial here was still 0 and 0. Okay, all right, my bad for that. So but anyhow, I hope you understand that part. Okay, that is after dissociation that you get these two concentrations. So then at equilibrium, your concentrations would be 0.01 minus 7.59 times 10 to the negative 4, and then here they would be simply 7.59 times 10 to the negative 4. I'll put those in brackets so that we don't get bogged down in numbers. 7.59 10 to the negative 4. So then we're going to go ahead and set up our Ka, because the calculation is asking for calculating Ka. So we don't know the Ka right now. So initially we've been calculating pHs, which was the hydronium ion concentration, but we already have that now. So then 7.59 times 10 to the negative 4, that's for the hydronium ion, and 7.59 times 10 to the negative 4, that's for the conjugate ion. You don't have to write it twice if you don't want to. You can just write it as squared. I'm just writing it so that you know what I'm doing. 0.01 minus 7.59 times 10 to the negative 4. That is your acid concentration now. So those are your concentrations that you have, and Ka turns out to be then 6.2 times 10 to the negative 5. So once you do all of these calculations here, so then pKa is equal to the negative log of 6.2 times 10 to the negative 5, which is then 4.21. So those are our two answers that we need for this problem. Okay, next one, the pH of a 0.164 molar aqueous solution of dimethylamine, the structure is given here, is 11.98. What are the Kb and the pKb, okay, for this base? So let's write the equation. CH3 to NH2 plus H2O, equilibrium. Now this is an NH2 over here, and since you're given pKb's, you know you're going to get hydroxide ions. So the conjugate acid of this base is CH3 2NH3. Remember, always just add a proton. Okay, that's how you get the conjugate acid. And then, of course, the hydroxide ion concentration that you have there. So initially, your concentration is 0.164 molar. And initially, these are both 0. I won't make the same mistake I did before. So anyhow, so 0 and 0 is what you start with. The change is going to be now where you are given the pH, okay, of the solution. So pH means the negative log of, antilog of 11.98. So you take that, but this is actually pH, so which means we need to find out the pOH. Okay, so one more step. So 14 minus 11.98, which gives us 2.02, that's pOH. And so then the hydroxide ion concentration is 9.5 times 10 to the negative 3 molar. Okay, I hope you got all of that. So this was pH. Okay, so first I calculated the pOH and then calculated the hydroxide, which is antilog of 2.02. So then my changes over here are going to be the 9.5 times 10 to the negative 3, and then 9.5 times 10 to the negative 3. Those are my new concentrations. And for the base, it's going to be 0.164 minus 9.5 times 10 to the negative 3. So, excuse me, making another mistake, okay, because that's going to be my equilibrium. So 0.164 minus 9.5 times 10 to the negative 3. That is my equilibrium concentration. This is the change. All right, so then this is 9.5 times 10 to the negative 3, and then 9.5 times 10 to the negative 3. Yeah, you probably know what I'm doing anyway, right? Okay, so then our Kb is equal to 9.5 times 10 to the negative 3, and I'll just take a square of that because you have two numbers of the same value, divided by 0.164 minus the 9.5 10 to the negative 3, and that is your concentration change for the base. This gives us a value of 5.8 times 10 to the negative 4. So that is our Kb value. Our pKb is negative log of 5.8 times 10 to the negative 4, which is then 3.24. Okay, so a little bit involved over here. Don't forget, if you're given the pH of a base, then you have to first find the pOH. Okay, so that's what I forgot to do here before. So find the pOH first, and then you do the calculations. Okay.